Good morning to all of you. I am going to read a chapter of physical chemistry. The second law of thermodynamics. Need for the second law of thermodynamics. First law of thermodynamics is the law of conservation of energy. There are several phenomena which cannot be explained by the first law. The first law is not sufficient and has certain limitations which are discussed as below. First law does not put restriction on the direction of flow of heat. First law establishes the relationship between the heat absorbed and the work done by the system. It places no restriction on the source of heat or on the direction of its flow. According to the first law of thermodynamics, it is possible to heat water using ice without any external effort. Yet we know from experience that such a transfer of heat from lower temperature to high temperature will not take place spontaneously. Heat is always found to flow from hotter to colder body. Thus, first law is unable to tell the direction of flow of heat. It indicates that if such process occur, then heat gained will exactly equal to the heat lost. Similarly, first law cannot predict whether a gas can diffuse from lower pressure to high pressure or water can flow uphill on its own or not. Thus, first law provides no information regarding the feasibility of a process. The second law of thermodynamics helps us to determine the direction in which energy can be transferred. First law has no criterion for spontaneity of a process. There are several natural processes which take place of their own in one direction only, but they do not proceed in reverse direction on their own. For example, water flows down the hill but cannot flow up the hill of its own. Flow of heat from water to colder body, expansion of gases into vacuum, burning of fuels, etc. are some examples of processes which take place only in a particular direction. Such processes are called spontaneous processes. According to law, it was suggested that decrease of heat content is the reason for spontaneity. This means that a reaction in which heat is evolved must be spontaneous, whereas a reaction in which heat is absorbed must be non-spontaneous. But there are some processes in which delta U is positive. Still, the reaction process spontaneously, such as vaporization of water at low pressure, H2O at 1.0 kPa, H2O gas 298 Kelvin temperature. Delta U is equal to 41.42 kilojoule per mole. Hence, delta U cannot be criterion for spontaneity. Similarly, delta H cannot be used for predicting spontaneity because there are many reactions which proceed spontaneously with the value of delta H. Positive value of delta H, dissolution of NHCl, NH4Cl in water. Thus, it is seen that function U and H derived from the first law of thermodynamics cannot predict the spontaneity of a reaction. Hence, there is need for second law. It is the second law of thermodynamics which define a new state function called entropy. Thus, function entropy along with other function like freeze energy Z is used to predict whether a given process is spontaneous or non-spontaneous. As stated by first law, the exact equivalence between heat and work is not possible. First law establishes the relationship between the heat absorbed and the work done by the system. According to the first law, when heat is converted into work, the work done is equivalent to the heat absorbed. While it is seen from experience that work can be completely transformed into heat, but heat absorbed cannot be completely converted into work without leaving some change in the system or surroundings. This observation cannot be explained by the first law. The second law helps us to calculate the maximum fraction of heat that can be converted into work for a given process. Thus, the first law of thermodynamics is not sufficient and therefore an additional law which explains the above limitation is necessary. Before taking various statements of second law of thermodynamics, we discuss what is a cyclic process and the Carnot cycle. Then various statements of second law of thermodynamics can be easily understood. Cyclic process. In a cyclic process, a system after undergoing a series of changes return to original state as shown figure 1. A system undergoes change from state A to state B by path 1 and returns to the original path by path 2. In this is a cyclic process. The net change of internal energy cyclic process is 0. Delta U is equal to 0. Therefore, according to the first law, delta U is equal to Q plus W. For a cyclic process, delta U is equal to 0 is equal to Q plus W. Q is equal to minus W. When the cyclic process is carried out at constant temperature, the cyclic is said to be isothermal cyclic. If the process is carried out infinite relatively small steps, the cycle is to be reversible cycle. Although reversible process is only imaginary and cannot be brought into practice, but the concept is quite useful in driving some important relationship. The most well-known cyclic process is Carnot cycle. The Carnot cycle was named after a French engineer, Sadi Carnot. He was interested in the efficiency of a steam engine and other heat engines, the devices which convert heat into work. He observed that maximum conversion of heat into work is possible in a cyclic process in which all necessary steps are carried out reversibly. Such a reversible cycle is called Carnot cycle, and an engine operating on the basis of this hypothetical cycle is called Carnot engine. An expression for the efficiency of a Carnot engine may be derived using a schematic diagram as shown in figure 2. The system consists of 1 mole of ideal gas has filled in a cylinder which is insulated and fitted with a frictionless piston. The gas is brought in contact with two heat reservoir sources at T2 and sink at T1, which are maintained at constant temperatures where T2. The Carnot cycle involves four reversible steps: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. These processes are represented on a pressure volume diagram. Step 1: Isothermal reversible expansion. The cylinder containing 1 mole of ideal gas having volume V1 is placed on the source. The gas absorbs quantity of heat 2 and heat undergoes isothermal reversible expansion to volume V2 indicated by curve AB. The work done W by the system is given as minus W1 is equal to RT2 ln V2 by V1. As in isothermal process, delta U is equal to 0, the work done is equal to heat absorbed. Q2 is equal to minus W1 is equal to Q2 is equal to RT2 ln V2 by V1. Work done by the system is taken as negative according to IPSC convention. Adiabatic expansion. The cylinder is removed from the source, kept on insulating base. The gas is allowed to expand adiabatically from volume V2 to V3. In this step, the temperature decreased to T1, the temperature of the sink. This path is known by a curve BC. The heat absorbed by the system is zero as expansion takes place under adiabatic conditions. The work done by the system W2 is given by minus W2 is equal to CV bracket T1 minus T2 bracket close. W2 is equal to minus CV T2 minus T1, where CV is heat capacity of ideal gas. Work done is negative by the usual convention. Isothermal compression. The path is shown along the curve CD. In this step, the cylinder is removed from insulating base and is kept in contact with the sink at temperature T1. The gas is compressed isothermally till the volume decreases from V3 to V4. The work done on the system is positive by convention and is given by W3 is equal to RT1 ln V4 by V3 as amount of heat Q1 having negative sign exactly equal to W3 will return to the sink. Thus we write minus Q1 is equal to W3 RT1 ln V4 by V1. Adiabatic compression. In this step, the cylinder is removed from the sink and placed on the insulating base and the gas is compressed adiabatically along the curve dA. The volume reduces from V4 to V1 and the temperature of gas rise from T1 to T2. The work done is positive by convention and is given by W4 is equal to CV into T2 minus T1. As a result, for operations, the system returns to its original state and a reversible cycle is completed. The total work done W in this cycle is given by W is equal to minus W1 plus minus W2 plus W3 plus W4. It gives the relation RT2 ln V2 by V1 plus RT1 ln V4 by V3. Net heat absorbed Q is given by Q is equal to Q2 plus minus Q1. RT2 ln V2 by V1 plus RT1 ln V4 by V3. Since point T2 V2 and T1 V3 lie on the same adiabatic curve BC and T2 V1 and T1 V4 lie on the same, then using expression Tv gamma minus 1 is equal to constant T2 V2 gamma minus 1 plus T1 V3 V power gamma minus 1 T2 V1 gamma minus 1 is equal to T1 V4 gamma minus 1. Dividing equation V4 by V3 is equal to V1 by V2. Substituting for V4 by V3, W is equal to RT2 ln V2 by V1 plus RT1 ln V1 by V2. Result total work done is equal to R T2 minus T1 ln V2 by V1. From the above derivation, it is observed that work done in Carnot cycle is only the work involved in the isothermal operation, because the work done in the adiabatic operation cancel one other. Efficiency of Carnot cycle and Carnot theorem. The efficiency of neta of Carnot cycle or heat engine is defined as the ratio of work done by the system to the amount of heat absorbed at a high temperature. Neta is equal to W by Q2. Substituting W and Q2 from equation 11 and 2. RT2 minus T1 ln V2 by V1 divided by RT2 ln V2 by V1. It gives neta is equal to T2 minus T1 by T2. From equation, it is clear that the efficiency of reversible heat engine depends only upon the temperature of source and the sink, and is independent of the nature of working substance. In other words, all reversible heat engines working between the same temperature having same efficiency. Also, the efficiency of a reversible heat engine is maximum for the given temperature. This is called Carnot theorem. The efficiency of heat engine operating in Carnot cycle depends only on two temperature at which the engine operates. The greater the difference between T2 and T1, greater is its efficiency. For a cyclic process, net heat absorbed is equal to net work done. Q2 minus Q1 is equal to W. Neta is equal to Q2 minus Q1 upon Q2. N is equal to neta is equal to T2 minus T1 by T2 is equal to Q2 minus Q1 by Q2. Equation name as 15. Two important conclusions arise from this equation. If T1 is equal to T2, no work done in Carnot cycle. This is more clear from the equation when T1 is equal to T2, then the work done in isothermal expansion at temperature T2 will cancel out the work done by the system in isothermal expansion at temperature T1. In other words, in Carnot cycle, no heat will be converted into work if isothermal expansion and compression above are carried out. It follows from equation 15 that efficiency neta of Carnot cycle will be unity if T1 is equal to 0, as T1 can never be 0. Therefore, T2 minus T1 by T2 is always less than unity. Hence, the efficiency of heat engine is always less than unity. Thus, only a fraction of heat absorbed at a high temperature can be converted into work. Statement of second law of thermodynamics. Having discussed below the cyclic of heat engine, we can now give the statement of second law, which can be easily understood from the efficiency of the Carnot cycle. Kelvin statement. Since T2 minus T1 by T2, it follows that W is less than heat absorbed. W is less than Q2. Work done is less than heat absorbed. This means that only a part of the heat absorbed by the system at higher temperature T2 is converted into work. The rest of it Q1 is given out by the system of the surroundings when it is at the lower temperature T1. Based on this observation, Kelvin stated the second law of thermodynamics. It is impossible to use a cyclic process to transfer heat from a reservoir and convert it into work without at the same time transferring it from hotter to a colder body. It also states that it is impossible to convert heat completely into work without leaving some efforts in the system or surroundings. Although the second law has been stated in a number of ways, but all these statements have the same fundamental concept. Work can always be converted into heat, but the conversion of heat into work does not take place under all the conditions. Calvin Planck's statement. We have seen that work done by a heat engine operating in a cycle is zero when the two temperatures are same. The Calvin Planck's statement of second law is: it is impossible for a system operating in a cycle and connected to a single heat reservoir to produce a positive amount of work in the surrounding. In other words, it is impossible to construct a perpetual machine which operates slowly by removal of heat from a thermal reservoir. Clausius statement: a heat engine operating in cycles can perform work only by absorbing heat from a reservoir at a high temperature and by rejecting the difference between heat absorbed and the work done by the engine to another reservoir at a lower temperature. On this fact, the Clausius statement of second law is based. Clausius statement of second law of thermodynamics is: it is impossible to construct a machine that is able to transfer heat by cyclic process from a from colder to a hotter body without using external energy. Thermodynamic scale of temperature. We are familiar with the construction of most commonly used thermometer containing mercury sealed in a glass bulb connected to a capillary tube. On this tube, 0 is read as the length of mercury column when in contact with ice, and 100 corresponds to the length of mercury column in boiling water. The length of mercury column between 0 to 100 is divided into 100 equal divisions. Each division is equal to 1 degree Celsius. This is Celsius scale of temperature. As this scale is based on coefficient of expansion of a liquid, therefore using different liquid in the thermometer will show different value of temperature for the same object. This problem got solved by the study of properties of gas. It was found that an ideal gas ceases to exist at a temperature of minus 273.15 degrees Celsius. This temperature called absolute zero. The temperature scale suggested on the basis of is called ideal gas temperature scale and is found to be independent of the nature of gas. Lord Kelvin developed a thermodynamic scale of temperature based on the fact that the efficiency of reversible heat engine is independent of nature of gas taken in the heat engine. This scale is found to be identical with the identical gas temperature scale. Consider a reversible heat engine operating between two constant temperature heat reservoirs. One of heat reservoirs act as a source and the other act as sink. The temperature of each reservoir on the new scale may be taken as proportional to the quantity of heat absorbed Q2 from the source or heat lost Q1 to the sink. Let Q1 and Q2 represent the temperature of sink and the source respectively. Then on thermodynamic scale we can write Q2 upon Q1 is equal to theta 2 by theta 1. Equation 1 gives the ratio of temperature based on ratio of quantity of heat exchange and is independent of the nature of thermometric substance. Take the reciprocal equation, become Q1 by Q2 is equal to Q1 by Q2. Theta 1 by theta 2. Subtracting from unity, 1 minus Q1 by Q2 is equal to 1 minus theta 1 by theta 2. Q2 minus Q1 by Q2 is equal to theta 2 minus theta 1 by theta 2. Q2 minus Q1 is equal to W. Q2 minus Q1 by Q2 is equal to W by Q2 is equal to theta 2 minus theta 1 by theta 2. This equation defines the efficiency of reversible heat engine in terms of Kelvin temperature. By putting theta 1 0 0 of new scale, we get Q2 minus Q1 upon Q2 is equal to W by Q2 is equal to 1. The 0 on the Kelvin scale is temperature of sink of a reversible heat engine having efficiency equal to 1, which means that such a cycle completely converts heat into work. This is possible only if the lower temperature to absolute zero, the ideal gas temperature scale. In fact, the ideal gas scale and Kelvin are identical provided the gas is ideal. The temperatures on the thermodynamic scale are expressed in terms of degrees Kelvin represented as K. Further, it has been found that if theta 1 is taken equal to 273.16 Kelvin, the triple point of water, then Kelvin and Celsius scale become identical. 273.16 Kelvin is equal to 0 degrees Celsius. Next term is entropy. The function entropy was established from the work of Carnot. Clausius in 1850 introduced this function of state S. For a reversible Carnot cycle operating between the temperature T2 and T1, the efficiency is given as neta is equal to Q2 minus Q1 by Q2 is equal to T2 minus T1 by T2, where Q2 is the heat absorbed isothermally at temperature T2 and Q1 is the heat lost isothermally at temperature T1. Rewriting equation, 1 minus Q1 by Q2 is equal to 1 minus T1 by T2. Q1 by T1 is equal to Q2 by T2. In general equation may be written as Q reversible by T is equal to constant, where Q reversible is the amount of heat exchange in a reversible process. Thus, we can say that the heat absorbed and lost isothermally and reversibly divided by the absolute temperature at which the heat is exchanged in a constant quantity for a given system. Equation 2 has been derived by taking positive sign for the heat absorbed Q2 and negative sign for the heat lost Q1. If Q2 is heat absorbed and Q1 is heat evolved, Q2 by Q T2 is equal to minus Q1 by T1. Q1 by T1 plus Q2 by T2 is equal to 0. Q cyclic is not equal to 0, therefore Q is not a state function. Summation Q by T is equal to 0. Thus, when the isothermal and adiabatic process in a Carnot cycle are carried out in finitely small steps, the summation of Q by T terms is equal to 0. Entropy is a state function. Consider a cyclic process ABA carried out reversibly. It can shown to consist of a number of small Carnot cycles as shown in the figure. The horizontal lines represent the adiabatic process while the slanting vertical line represent isothermal process. By making each Carnot cycle extremely small and increasing their number, it can be made to correspond to continuous curve ABA. The reversible cycle can be considered as being made up of infinite number of Carnot cycle. For these cycle, we have summation Q by T is equal to 0. When the change are made in finite small amount, we can write as delta del Q by T is equal to 0. For a cyclic process from performed in a two-step from A to B and back B to A, we can write as summation A to B del Q by T is equal to minus summation B to A del Q by T. Q by T A to B is equal to minus Q by 2 B to A. It follows that Q by T is a definite quantity whose value depend only on initial state A and final state B and is independent of path followed for the process. For a reversible process, we can write quantity Q by T as Q reversible by T. Thus, we conclude that the quantity Q reversible represent as a state function. This state function is called entropy of system and is represented by S. Thus, S is equal to Q reversible by T. Entropy is an extensive variable and is defined only in terms of differences. The change in the value of entropy in going from one state to another and is independent of the path. Delta S is equal to SB minus SA Q reversible by T, where SA and SB are entropy in state A and B of both systems respectively. As entropy is a function, a small change in its value can be represented by an exact differential ds. Hence, we write ds is equal to q reversible by t. Unit of entropy. Entropy change is expressed as delta S is equal to q reversible by t. Entropy is expressed in terms of joule per degree. When heat is expressed in calories, then entropy is reported as calories per degree. Further, entropy is an extensive property. It is therefore necessary to mention the amount of substance involved. Usually it is expressed for 1 mole of substance. Hence the unit of entropy are calories per degree per mole. When heat is measured in joules, we write the unit of entropy as joules per degree per mole.